通じてない How's it? Can you hear me? なぬちゃんと言ってないといかんのかなハローどうしますsorry, so how then cannot answer me? So then, okay, I become the session chair. So,
Okay.
So the next speaker is Professor Tomoki Nakanishi from Nagoya University. The title is Cluster Algebra. Please start.
Thank you very much for invitation. And I'm talking on cluster algebra. See. So my research, first of all, I'd like to introduce my research topic, theory and applications of cluster algebra. And I'm a mathematician with a mathematical physics background. And I first explain my research history briefly. So after getting my PhD, 1990, I have been working on algebraic structure of integrable systems in quantum statistical physics in view of quantum groups. So our keywords are Yang-Baxter equation, conformal field theory, finally algebras, and quantum groups. So as an organizer asked me some relation to quantum system, and my research background is strongly related to this quantum mechanical and quantum field theory system. And then I somehow switched my subject around 2009 to the current working on this theory and application of cluster algebra. There is some natural continuation of subject which I also want to explain. Okay, so I guess many of you have never heard about this concept cluster algebra. So I somehow start to explain it very briefly. So what is a cluster algebra? So in brief, they are introduced around 2000 by Russian-American mathematician Sergei Fomin and Andrei Zerebinsky. So you see, this is a 21st century mathematics. And so briefly speaking, they are a class of commutative algebras, and which originate in Lie theory. And prototypical example, I just give a keywords. For example, coordinate rings of Grassmannian or special linear group. They are some basic object in Lie theory. However, this concept is not totally new things as many other things in mathematics. They have some roots, and it come back to the Euclidean Thoreau's theorem in Euclid geometry. It was discovered first century. So it's a very old subject. I recall you what is Thoreau's theorem. So when you have a circle, you have 4 points. We have a square, and let A, B, C, D be the lengths of these edges, and we have diagonals. Let's say EF be the length of these diagonals, and they satisfy the following algebraic relation. EF is equal to AC plus BD. When this is a rectangular, it comes back to the Pythagoras theorem. So it is a generalization of Pythagoras theorem. And you see there is some algebraic relation here, which is in fact a typical example of the relation in cluster algebra. So it's it's already known, but as a recognition as some unified notion is new, and it is quite useful. And after the introduction, it was actively studied, and nowadays they are considered as some common underlying algebraic and combinatorial structure appearing in several areas of mathematics. So naturally, it also appears in mathematical physics too, and in classical and quantum systems, okay? So from my point of view, classical and quantum is the same, both are kind of related concept. So I really don't especially quantum case, but the classical case is also interesting. Anyway, since this is a workshop for quantum system, I give some mathematical physics example, especially in quantum case. I mean, it's relation, the subject which is related to cluster algebra. There are many, but I only give 3 things here. You don't know the word, but don't please ignore, just give some keyword. There is a so-called T and Y system, some algebraic system. Also, there is so-called dilogarithm identity in conformal field theory. This is a very thoroughly studied quantum field theory related to string theory. Also, those systems are related to integrable spin change. It is a quantum mechanical system starting by Heisenberg, and especially like XXZ model. It's very familiar model in quantum physics, yes? And so the second subject, which is strongly related, is a Schrödinger equation. You know, it's obviously it's related to quantum mechanics. And there is so-called Stokes phenomenon, yeah? And this is related to so-called WKB approximation, and it's a theory called exact WKB analysis. So it's also a quantum mechanical system. And finally, I want to mention that in a string gauge theory, or gauge theory, there is a notion so-called mirror symmetry, and also cluster algebra are related to these things. Okay, and brief explanation of why this cluster algebra is so much appearing in several areas. Well, actually, there are similar structure in mathematics, which is algebraic and combinatorial as well. It is called root system. And I will explain it more later, but the root system is a generalization of a symmetric group, which is just a group of permutations. It's fundamentally important in mathematics and physics. It's just system of a discrete system, right? Discrete theorem. And so it was summarized as a root system, and I think it is itself is a great discovery of mathematics in 20th century by Early Carlton, also maybe Hermann Weyl and Coxeter, Blueberky, and so on. And this cluster algebra is a kind of sister or brother, whichever theory. It's a kind of a relative of this system. And so that's a fundamental structure. So that's why it appears in several things. Okay, let me give some very prototypical example to give you a feeling why it is interesting. So without any background, I just explain, I consider some discrete dynamical system. Okay, so you just follow me. Yeah, x1 and xp, any formal variable. It's just numbers which take, say, a value in real line or whatever. And we consider the following discrete dynamical system. Discrete means the time is discrete time, not continuous, but time is 0, 1, 2, and so on. And it developed as following. We have following initial condition at time 0. Yeah. So we start at given, say, value, say real number, x1 or x2. Okay. And after that, we have the following type development. For it depend on your time is even or odd. And even case you just x2 does not change, while x1 is given by the following simple rule. Describe this one. So x1 is inverted, then in the numerator x2 plus 1 is put. Okay, so you have something new. And for odd case, you just exchange the role of 1 and 2. And you continue. And let's observe what will happen. Yeah. So far, is there any question about this system? Okay, I can continue. So I calculated it up to at time 5, but let's closely look at what will happen. So as you see, these are our initial values, okay? And when you make a development, this is time is even, so we do this calculation as explained, yeah. While x2 does not change at all. Okay, so next, when you go from 1 to 2, you change the load of 1 and 2. So this time x1 does not, it's a constant. It remains the same. While at x2, you first of all, x2 is inverted, yes. And here, I have already loaded this one is this one plus 1, yeah. So sorry. Okay, I'm not accustomed to this. Okay, so it is x1, yeah. And so we have these things. And so far, nothing interesting happened. You just summarize it as a new variable or new value, okay? So let's do once again. So it is even number. So now x1 is kind of, say, it changed. So this one is now inverted. And you have to do this calculation. So you then make plus 1, okay? So x1 is now appear here due to this one, okay? And so this is so this whole is a numerator, okay? Now, as you see, we have something good happen. So x1, x2 plus, it's a school mathematics. So factorization occurs. Moreover, the factor cancels. We also have some cancellation here. So as a result, we have somewhat simplified our expression here. Now let's continue. Okay. From 3 to 4, our x1 does not change. On the other hand, x2 is now inverted, and the numerator is, you just add plus 1 here. So you have these things. Okay, now it's something nice happen again. So this explanation mark here is good things happen. So we mean, I mean, these are canceled, and it comes back to the original value. Yeah, great. And do it once more. Now x1 is, sorry, x1 is, it is inverted here, and adding 1 here, you have this one. And once again, we have, so we have explanation mark here, cancellation. And x2 remains the same. Okay. So now after 5 times, you have a complete periodicity, I mean, except for the interchange of 1 and 2. Okay, so we observe this simple dynamical system has nice periodicity, which is not expected from the beginning. And also, we somehow we have several reduction, and always denominators are canceled to monomial. You can see what I mean is here, for example, yeah, or here, always canceled. Okay, so and as a resulting, our things is called Laurent monomial. So it is called. So that's why it is called Laurent phenomenon. And moreover, as you see in the above expression, there is no negative sign at all. And so it is called positivity. It is not obvious at all. So because even let me come back as a previous stage, here we have no negative signs. Yeah. However, when you have an expression of positive signs and divided by the positive polynomials, it may happen that the reduction could be negative polynomials with negative signs. Yeah, and we did this reduction various times, but still there's no negative sign at all. And this is a kind of feature of cluster algebra, and those features are very special properties. Okay. I also want to give some feeling about this periodicity, so I give a geometric interpretation of this. Yeah. In fact, it is an interpretation by Thoreau's theorem. Yes. So just by consider pentagon. Yeah. Here. Okay. And let's consider h, x1, and x2. Yeah. And somehow let's attach variable here. And for simplicity here, we consider all other outer edges of a pentagon is 1 here for simplicity. Yeah. So now we make a so-called flip in this quadrilateral, and we have attached the, sorry, it's x1 prime, yeah, and those are this diagonal, and Thoreau's theorem says those lengths are related by this, which I have already explained at the beginning. And so we do this flip alternatively, namely if next time we flip this diagonal to the other one, yeah? And next time we keep this and we flip 1 and so on. And we continue and 5 times. And after that, we recover the same triangulation with the original one. However, but those index are interchanged. Yeah. So this is the same periodicity. And in fact, this explanation already explained what happened in the previous pages. In fact, you can generalize this to more general things. So you replace this length to ABC, for example. Then Thoreau's theorem says that this factor is B here, and this is AC. Yeah. And even for these things, the previous page calculation can be done in a similar way, and final result have the same periodicity. This, in fact, picture present the proof. Yeah. So, I'm going to explain in the next session how to generalize this to cluster algebra. So let's see. Sorry. I want to go to the next page, but I don't know. Okay. Okay. And one more thing. I want to close my first session. Its relation to root system. So this is a simplest example of root system called type A2. You don't have to, you just accept this diagram is a root system of type A2. We have 6 vectors on the plane, and it is a geometric realization of the symmetric group of degree 3. So it is a group of permutation of 1, 2, 3. Why it is so? So we have alpha for the vector, we have the perpendicular surface here, and we can consider a reflection with this. And similarly, we have this one. And for each hyper surface, hyperplane, you consider a reflection. And for alpha 2, yes. Then we see that x alpha and x alpha 2 reflection generate as a group, which exactly in S3 correspond to the transpose of numbers 1, 2, and 2, 3. So they are generator. So I recall what I obtained in last in the previous pages, say here, and so it's rather dirty now, but we have several things we obtained by this calculation here. So we just correct those here. So these 2 are initial variable, while these 3 things are obtained after this time development. And somehow we have some relation to this diagram. Where can I see it? We have, you look at the denominator, and somehow we identify this as, so this vector is called a root, by the way, and is identified to this. So there is now a root system hidden relation to root system now appears, and in this by this reason this is called cluster algebra of type A2, and this is the simplest non-trivial example of cluster algebra. Okay, maybe I stop my first session now. What should I do?
Okay. Any questions or comments? Okay, I have a question.
Sure.
If you have a cluster algebra, can you build from a cluster algebra some invariance of manifolds? For example, this sum of 3 manifolds.
Yes. You asked me, is there any relation to cluster algebra to what kind of manifold? I couldn't.
For example, the trivial this sum.
So what is it? I can't hear you. Yeah.
State sum of a 3 manifold trivial type state sum.
Hayashi-san, could you repeat the question? I somehow
sorry, I can't hear. Sorry.
Can't get you. You can write somewhere. Sorry, I just can't recognize the word. Maybe I know, but I just can't hear you.
Okay. You showed a relation between the cluster algebra and the pentagon relation, right?
Pentagon. Yes.
Yeah. The partial relation play an important role in the construction of certain invariants of manifold called the state sum.
That's Dixon. Could you spell it to me?
STATE. SUM.
Sorry, sorry.
You can type. I think you can type in the chat room. There is a.
Okay. Yeah, that's good. I will check.
I think I already typed that.
State sum of 3.
Try Bureau. Okay, I recognize the name. And okay, a state sum of 3. Okay, thank you very much. So it's related to say link polynomial and those things, right? As far as I understand.
Yes.
And you said pentagon ratio is somehow close related to this construction. Yeah. That's what you said. I don't know it. I don't know its relation. Maybe it's an interesting problem. Unfortunately, I don't know it's related or not.
Oh, that's okay.
Great.
Any other questions?
Sorry, I have one question. So, could you show back to the 7th slide, previous slide?
This one?
Yes. So you explain the cluster algebra by using this picture. But you explain cluster algebra by using this picture. However, I could not find what is the element of cluster algebra.
Okay, that's a good system, a good question. Actually, I never explained to you, and so I just explained cluster variables, and cluster algebra itself is an algebra generated by these 5 elements. It's a commutative algebra, and so you asking a very right question, and I just explained that these 3 variables have some connection to this one, but there is some mismatch. You know, there are 6 vectors here. We have 5 variables. And somehow you identify this one to minus alpha. Yeah, naturally. I just taking. So, Hayasa, I'm not really asking your question precisely, but I somehow explain that this is an important point. So, correspondence to the root system is not perfect, you know. So that's why I said this is a sister or brother theory. So generally, those are briefly speaking, cluster algebra can be identified as a part of the root system, and its connection is not completely understood yet. But this is one of the general features that cluster algebra is related to root system. At this moment, I only answer in this way.
Okay, thank you very much.
Okay, any other questions? Okay, I think it's time to continue our talk.
Okay, so now I'm going to give a formal definition of cluster algebra. Yes, and there are 2 important notions in cluster algebra. Yeah, so one is called seed, the other is called mutation, and those together we have can construct a cluster algebra. And in fact, it is a generalization of what I have done in this simple pentagon dynamical system. So first of all, we fix a rank, which is just a positive integer. In a previous case, it was 2, but we can consider n. And seed, first of all, is a concept. It's just a pair of two things. First one is called exchange matrix. It's just a matrix, n by n, square matrix, which is a skew symmetric, and integer components. So skew symmetric means this relation. For example, when you choose rank 2, we skew symmetric matrix always have such form. So this is a general choice. You can take any of it as you like. Now, the rest part, a cluster, is just a gathering of number variables. That's why it is called cluster. And it is just n tuple of algebraically independent variable, like x1, x2 in the previous cases. Now, having seed, you make a mutation. Okay, mutation to n directions. I first give some conceptual diagram. So we have seed here. You can make a mutation to say 1, 2, 3, 4, 5 directions. For example, if your rank is 5, and you can repeat this mutation to as many as you like, and you obtain a dynamical system on trees, on tree, Tn, say regular tree. Okay, and I describe what is this mutation rule. We introduce a function which just a function, graph is something like it's just called a positive part. And using this function, you change your cluster variable according to your exchange matrix, and exchange matrix used here. And among n, only the variable at k is mutated for this mutation k, and other variables stays the same. We see it already, these things. And general structure is as follows. So you just take the inverse of the original variable. We see it already. And in the numerator, you have such binomial determined by your B matrix. And you have something new. And interesting things about this cluster algebra is not only this variable, but this exchange matrix itself also changes. So this B is kind of a DNA of this development, but the DNA also a little bit changed. So that's mutation, yeah. And the rule is somewhat kind of looks complicated, but so I don't explain, but there is some rule describe this one. And it turns out this rule is very, very useful, interesting, and it gives a various result. So just a cluster algebra only use these definitions. And it's a great discovery by Formy and Zerovinsky that if you have such systems and you have a lot of interesting common phenomena happens. And one thing I want to mention is involution property. It means if you make a mutation first, and if you mutation once again for the same directions, and it go back to the original one. So this attachment to these trees labeled by these numbers makes sense. Okay, so this is a definition. And let's review what I have done. So this is just the same equation in the last pages. I just write it once again. And type A2 is one which I explained in the previous example. So what is the simplest non-trivial skew symmetric matrix? It is this one. Okay, and we have two independent variable, and we make a mutation, say to the actual one, using this formula. It's not important, but this one is applied now. So we have just minus of b. This is b prime, and x prime. Looking at this carefully with this positive functions, and only this one contribute and this does not contribute, and we have exactly this equation, and we have already seen this. So so we repeat this mutation, but if you mutate at the same one, then it go back. So you have to do it alternatively to have some non-trivial development, and that's what I did. You know, even odd times we change the role of x1 and x2, and we know that after 5 times this x5 come back to original one. And I want to show you there is a efficient Java applet by Bernhard Kehrer working on cluster algebra. It is called quiver mutation. And if you want to do try some more, you can use this applet. I demonstrate you. Moment, please. Here. So now this is so-called quiver. It is a graph which corresponds to our choice of skew symmetric matrix, and it's not so important anyway. You can calculate your the calculation which I did by hand with this applet x variable like this. Yeah. So a mutation is just done by pushing this vertex, and you have at 5 mutation you have here. Next, so note that this quiver changes the arrow which corresponds to the mutation over B matrix. Yeah, and we do mutation here, and we have something new here. Only mutated variables are appear here. Okay, and we do continue 5 times. And we come back. So this is a periodicity we have observed. Maybe we want to work more. So we add some nodes, which can be easily done here. Okay, now let's consider the following example. We add arrow. This corresponds to some choice of 5 times 5 square matrix of skew symmetric type. And I want to make a mutation to this. Okay, so variables like this. I will do mutation first 1, 3, 5, even odd numbers, then odd vertices. And then after that, we make a mutation for 2 and 4. Okay, and I repeat this several times. Let's start. So 1, 3, 5. Sorry, 5. Yeah. So each time you have some new variables. 2, 4. Yeah. It becomes complicated, but it's always Roland monomial. okay, and so Laurent polynomials, and I repeat this cycle. So 1, 3, 5. Now it becomes complicated. 2 and 4. Okay, still I continue. 1, 3, 5, and 2, 4. Okay, now it becomes simplified again. So 1, 3, 5, 2, 4. Now we see that the value going back, but 1 goes to 5 and 2 goes to 4 and 3. So it's interchanged. So this is once again a periodicity. Periodicity is an important relation between cluster in a cluster algebras. Okay, so this corresponds to the type cluster algebra of type A5 because what you see is actually a so-called Dinkin diagram of root system of type A5. Maybe one more example. Okay, so we add new nodes here, and we add arrows from here to here. Yeah, if you know the root system language, so this corresponds to the root system of type E6. Okay, I can do the same things. I mutate 1, 3, 5, then 2, 4, 6. So odd and even repeatedly. But if you do it, I've checked this before my talk, and computer easily stop because there is no enough memory to store the expression of Laurent polynomials. Okay, so instead of calculate a polynomial, we just calculate the numbers by putting initial numbers 1 always. I mean, specialize this variable x1 to x6 to 1. Or then the calculation becomes just a manipulation of integers. So there is no problem. Our computer can do it very easily. So this in program, it is called numerical X variable. And it asks you initial values. I put 1, 1, 1 everywhere. Okay. So let's make our mutation along the rule which I mentioned. So I first do mutation at 1. And this 1, 2 means it was previously 1, but now it becomes 2. So value is 2. Just the last digit is new values. I continue. 2, 4, 6. So this is a first cycle. And, you know, the initial value now becomes 2, 2, 2, 5, 5, 3. Yeah. Let me continue several times and see what will happen. Yeah? By the way, can you guess what will happen? Okay, you have answer in your mind, and let me repeat this several times. Okay. And 2, 4, 6. So now a new value is 338, 323, 23, 13. Sorry, 38, 23, and so it's rather big numbers. But let me continue. 1, 3, 5. Sorry, 5. Yes, and 2. I have to be carefully do it. Yes, now number becomes the largest number is 181. So the polynomial have 181, and a computer now have a trouble of dividing this, factorizing and divide these things in the memory. That's why it takes so many times and in computer. Now I can do it. Continue this. 1, 3, 5, 5. 2, 4, 6. 6. Yeah. Okay. Be patient. Do 1, 3, 5, 2, 4, 6. Okay. Good thing is now the number begin to reduce. It means this reduction start to occur. And let me repeat. 1, 3, 5, 5, 2, 4, 6. Now number become very small. 3, 9, 3, 2, 2, 2, 1. Let's do it once again. 1, 3, 5, 2, 4, 4, 6. Now all numbers becomes 1. So it shows the periodicity. Actually, I did this for 7 times. And 7 is related to so-called Coxeter number of this thinking diagram, but I don't explain. Okay, so you can experiment by yourself more about this, but I go back to my slide. But do you have any question about this applet at this moment? Because once I come back, I can't come back to these things.
없긴 하구나.
Okay. So.
그러니까?
Okay. So in fact, I'm going to summarize my talk. So there are, I just show some example, but there are several interesting properties of cluster algebra. Okay. So first of all, Lorentz phenomenon. It's okay. Not very difficult to prove, but it always happens for any mutation. Excuse me. Someone speaking. Okay, so also positivity, as I explained, happen, and this is really a very non-trivial fact, but it is now proved. And also relation to root system, but it's not very clearly understood yet. So this is my future problem. And also, I don't have any time, but a nice feature of cluster algebra. For me, this one is most important. So there's so-called tropicalization and detropicalization phenomena happen. And I can't say much about this, but briefly speaking, we have Lorentz monomial, yeah, and it's very complicated. Even a computer cannot prove it after 6 or 7 times of repeating mutation. But tropicalization means you just take the some how to say leading term of this Lorentz monomial, and then from this leading monomial is uniquely determines those Lorentz complicated Lorentz monomial, and this one future is very important and very non-trivial, but nowadays it is proved. And or as I mentioned, it appears in many things, various subjects, and also I want to mention that there is a quantum version exists. It is called quantum cluster algebra. Quantum means now it's commutative variable becomes non-commutative variable by canonical quantization, and every good things is preserved for this quantum case. And it is not known and studied, but it might be possible to apply them to information theory, for example, especially in view of this tropical property, because very complicated things can be kind of encoded to this tropical part, and you can recover this complicated things just by this tropical things. So you may use a key for coding, for example. I don't know much about it, but it will be interesting to have such application. I especially mentioned this because it might be some of you interesting. Okay, so I finished my talk. Thank you very much.
Okay.
Howden? We are Howden. So now we have a second question time. Do you have any question?
Oh, sorry. I didn't open my sound. I see a lot of things, but nobody can hear. Okay, I'm here. Oh, okay. So thanks our speaker. Any questions?
Yeah.
Okay, I have a question. Can you turn to the app, please?
Operate, yes.
Yes. If you change the order of the fixed node, so the period remains same or something else.
If you ask me if you is there any other periodicity? That's what you asked.
Yeah. The periodicity depends on the order of nodes. You
Okay.
push the nodes 1, 3, 5, 2, 4, 6, right?
Thank you very much asking you. Okay, first of all, if you put it randomly, you don't have any periodicity. Periodicity is a very rare occasions, and it's a relation in cluster algebras. And so my answer is you need to select very carefully some special mutation sequence, and only that case periodicity happens. But from a given seed, there are several different sequence mutation which possess different periodicity.
Okay.
Mm-hmm.
Okay. So if you change the order by 1, 2, 3, 4, 5, 6, what is the periodicity?
Okay.
Period.
So periodicity doesn't happen even if, moreover, this quiver, which represent exchange matrix, it also changes a lot.
Okay.
Okay, so it's not a kind of a stable dynamical system, but much more complicated things. If you're lucky and okay. By the way, I somehow want to change my answer. For that particular case, there are only finitely many possible seed occur along this all possible mutation. So if you insist some repeated mentions, 1, 2, 3, 1, 2, 3, whatever, because there are only finitely many seed, eventually come back to the original seed.
Okay, I see.
However, this one is very special because we start from this special choice of diagram which correspond to the Dinkin diagram of root system. Otherwise, we don't expect any good periodicity at the beginning.
Yes, I see. Thank you.
Mhm.
Any questions? Okay. No, if no question, let's thank our speaker again.
Mhm.
Okay.
Thank you.
Thank you.
So then next speaker is Kondian. I think could you prepare your slide?
Oh yeah, sure. All right. Let's see. Can you see it? Let me make it full screen. Can you see it?
Yes.
Yes.
Can you see the green color when I highlight the two words?
Yes, I can see green.
Okay. Okay. I don't have a pen, so I probably need to use a mouse to highlight some words. Okay.
中西さんお願いします。プロフェッサー中西？He already quit.
So I guess, does everybody know the rule of for chairing the next talk?
Yes.
You probably need to remind them.
中西さん、プロフェッサー中西。Could you take a role of session chair? Okay, I will take a session chair again.
Yeah,
So,
maybe you can remind the people the rule in the
okay, so I already mentioned that
Okay.
once you speak your talk in the next session, you need to be the session chair of the next talk, next session. So in this way, we can take a session role with opposite side. So I want to make more collaboration each other between Nagoya and SUSTech. So, but maybe he take a rest. Okay, I will make the session chair again. So the next session is Professor Liang Kong from SUSTech. His title is Boundary Bulk Relations in Topological Orders. Please start.
Okay, so thank you for. Oh, can you hear me?
Yes, of course.
Okay, good. All right. First, I want to thank the organizer for inviting me. Okay, so I'm gonna talk about boundary block relations in topological orders. Okay. I have trouble to turn the page. Okay. So the relation between the physics of the block and that of the boundary play a very important role in quantum field theory and also quantum gravity as well, and the condensed matter physics. Okay. So this relation have many names in different contexts with a different meaning. For example, holographic principle or holography, or open-closed duality, boundary block boundary correspondence, or boundary block relations. Extra. Okay, there are many names. So in this talk, I will review one of the manifestation of this relation. Okay, it says that the block is the center of the boundary. We will provide a formal proof of this statement and provide a more complete and precise mathematical formulation of these relations, and discuss its significance in the study of topological orders and the topological phase transitions. Okay. So holographic principle was first proposed by 't Hooft in 1993. It was believed by many physicists as a fundamental principle in physics. It says that the information of the universe scale as the area law instead of the volume law. Okay, and it also means that the information inside a three-dimensional disk. The 3D is always means spatial dimension. Okay, 3D disk in space can be encoded by the information living on the boundary of the disk. In other words, the boundary determines the block. Okay, because it encodes all the information of the block. We will also call it the boundary block duality or boundary block relations. Okay. All right, there are many examples of this type of boundary block relations. The first one I know is Wheaton's Chern-Simons theory, proposed in 1989. It says that if you have a three-dimensional Chern-Simons series, on the boundary of the theory, you get a two-dimensional CFT. Okay. The relation between these two is also kind of a holographic because the CFT sort of determine the Chern-Simons theory, Chern-Simons TQFT. I think the holographic principle became very popular after the discovery of ADS5 and the CFT4 correspondence by Maldacena in 1997. After that, there are many more ADS CFT or gravity gauge correspondence were discovered afterwards. Okay. And another source of example is in the conformal field theory or topological field theory. I would just abbreviate it as TQFTs. Okay, we will focus on this part of in this talk. Note that, but even though we focus on this, actually we're not going to talk about ADS CFT correspondence. But it's important to know that the ADS5 and the CFT4 correspondence can be understood as a part of the so-called open-closed duality in string theory. Okay, that's how the ADS5 CFT was originally derived from string theory. Okay, so in rational CFT, that means CFT just abbreviation of conformal field theory. This condition implies that the box CFT is the center of the boundary CFT, which is not unique for the given box CFT. Okay, once you give the box CFT, you can have many different boundaries. We will explain this fact. So this fact is just boundary is the center of the boundary in details. We start from 1 plus 1D TQFTs. Okay, I want to point out that I will start from 1D TQFT because I already view TQFT as a special case of CFT. Okay, CFT means conformal field theory. TQFT means topological field theory, and by definition, TQFT is automatically a CFT because it's not only conformal invariant, it's also topological invariant. Okay. All right. So if you look at the fully extended 1 plus 1D TQFT, there's a well-known results. The boundary TQFT is given by a matrix algebra. Okay, n by n matrix. Okay, the associated block TQFT is given by its center. Okay, just ordinary center. Take the center. The center is trivial. Okay. So in this case, we obtain the block is center of the boundary immediately. Okay, and in this case, the notion of center is the ordinary one. It's the one you're familiar with. But I want to explain this notion in detail. Okay, so the center of algebra is defined as follows: given algebra A, the center of algebra. Well, this is sort of well known, right? Just the center of algebra consists of all those elements which commute with every element in A. Okay. So that's the Euro definition of center, but this definition of center is not very good for modern applications. Okay, so we would like to give a better definition via the so-called universal properties. So I'm going to talk about the universal property of the center. All right, we need some preparation. Know that the multiplication map M. Okay, the multiplication map M is defined by just multiply them. Okay, just multiply the elements, because notice that ZA is a subset of A. Okay, so this is well defined. Oh, sorry. The important thing is that this map is an algebra homomorphism. Okay, let's record what the meaning of algebra homomorphism. So given the algebra homomorphism from algebra A to B, it means that this linear map should satisfy this condition. Okay. That's the meaning of algebra homomorphism. Oh, well, there's another one, you know, have to preserve the unit. But we, for now, I just want to emphasize this one. Let's expand this condition, okay? Let's expand this condition in this case, okay? So it means that M, so there are double F here on this side, right? Now replace F by M, you got M, the 2M, okay? M just means multiply them, right? So on this side, you got a ZA times Z prime A prime, okay? On the other side of this condition, okay, FAB now replaced by M of this element. Now you multiply them together, you multiply these two together, you got a Z and a Z prime first, tensor A prime. Then you do the multiplication, you got this one. All right, look at this two condition. Okay, look at this side and this side. Now take a special case, Z equal 1 and the A prime equal 1. What do you got? So that means this equal 1, this equal 1. Only thing you got is this, okay? And only thing you got this one. Now, what you got is that you got this. This condition holds for all A, okay? What does this mean? This means that this just Z prime must leave in the center, okay? So it also says that if Z prime indeed in the center, then this is an algebra homomorphism, okay? But in general, this multiplication is not an algebra homomorphism unless A is commutative. In general, this multiplication map is not an algebra homomorphism, okay? But if you replace one of them by A, then it is. Okay, after this preparations, we can, I'll state another properties. These multiplications have the following, making the following triangle commutative. What this triangle means, so this map, A map to ZA tensor A is defined by A maps to the tensor, map to the unit of ZA and tensor A. But well, you know, unit of ZA is nothing but the unit of A. Okay, it's the same identity element. Okay. Now you do the multiplication. You do multiplication, you simply multiply this two, right? This is identity, this is the A. So multiply them, you got A. So that means this triangle is commutative, okay? Element A mapped to A through this composed map. On the other hand, this identity map also map A to A. So this triangle is commutative, all right? All right, so we draw important conclusion is that the universal property of the center. So now I'm not gonna use the set theoretical definition of the notion of center. I'm gonna show you the universal property. So it means for any algebra A, any algebra X, okay, and any algebra homomorphisms F, which map from X tensor A to A, rendering the following, rendering the triangle commutative. By the triangle, I mean similar to this triangle. I mean, if I draw it explicitly, it will look like this triangle, okay? So assuming F is the map rendering this triangle commutative, then there exists a unique algebra homomorphism F prime from X to ZA, okay? On this side is just the identity of A and making the following whole diagram commutative. Okay, this is a universal property. It says that the triangle is the universal one. So this triangle is a universal one among all the triangles. So it looks, if you haven't seen this before, it might look strange to you, but it turned out that this is an equivalent definition of the notion of center. Okay, actually a better way. Okay, if you're familiar with the categories theory, the universal property of this is always a beautiful way to define a notion, and not only a beautiful way to define a notion, it also tell you how to use it. Okay, so it's a very powerful definition. By the way, you probably wonder where this F prime come from. Okay, from X to ZA. That's very easy to construct because you have this F map, right? Now you simply restrict this F map by restricting this factor, the second factor, to the identity of A. Okay, then you obtain a map from X to A. Okay, then you obtain a map from X to A, right? Then you show that the image always lie in the center. Okay, you can show the image always lie in the center. Then that means this F prime is actually a map from X to ZA. That's the one you're looking for. Okay. So that's the universal property of the center. Why it's important? Because although the ordinary notion of center is very simple, right? But the universal property is also very simple. But what is important is that it shares all this center share the same universal property with all the other notion of centers. In mathematics, for example, the Greenfield center, Milgren center, full center, Eden center, or Hausdorff cohomologies. Hausdorff cohomology can be viewed as some kind of derived center. This is why they all called center, because they share the same universal property. The only thing different is that they are centers. They're the same notion, but in a different categories. Okay. For example, if you replace A by a monoidal category and replace M as a monoidal functor, then the same universal property imply that this center is a Drinfeld center. Okay, but the universal property is the same, right? Okay, so that's good. So I discussed the 1 + 1D topological field theory, right? But are there any other manifestation of this boundary block relations? I mean, the block is the center of the boundary. Yes, indeed. In higher dimensional topological field series, instead of instead of study the TQFT directly, it's more convenient to consider topological orders, whose low energy effective theory are TQFTs. Okay. So some brief introduction of this notion of topological orders. So this topological orders is a gap to quantum physics at 0 temperature. Before the discovery of fractional quantum Hall effect, a gap to quantum physics was regarded by many physicists as a trivial phase because all the correlation function. Because all the correlation function decay exponentially. It seems that there's no non-trivial observables in the long wavelength limit. So people will think about this as something trivial. So it was a great discovery in the 80s that such a system is actually non-trivial. For example, such a system can have a non-trivial ground state degeneracies on surface with non-trivial topology. Okay, it was discovered in 80s. And also they have a non-trivial topological excitations, which can be fused and sometimes braided. For example, 2 + 1D topological order can be described up to an invertible topological order, okay, up to some minor thing, by the fusion and braiding property of anyons. Okay, anyons are point-like or particle-like topological defect in the 2D dimensional, 2 spatial dimensional topological order. Okay, and this kind of particle can be braided and can be fused and braided in 2-dimensional plane. So this fusion and braiding properties of anyon form a mathematical structure called a modular tensor category. Okay. So this modular tensor category also gives a mathematical description of the 2 + 1D topological order. All right. All right. A topological order is called anomaly free if it can be realized by a Hamiltonian lattice model with a local interaction in the same dimension, and is called anomalous if otherwise. Okay. Anomalous topological order must be realizable as a gapped defect in a higher but still finite dimensional lattice model. Okay, illustrated below. But if the lattice model is infinite dimensional, of course we can regard them as a non-existing model. It's not physical, right? Okay, so if otherwise, it's safe to say that such a topological order does not exist. Okay, now we want to do a so-called dimensional reductions. Okay. So consider a topological order realized as a defect in a higher dimensional lattice model as drawn in this picture. Can you see the mouse? Yeah, this one. Yeah, I highlighted here. Okay. Now what you do is that you drag, you pick out this bullet and you stretch it away from the screen. Okay. Then everything else becomes cigar shaped, like this one, pictured in this way. Okay. You pick out the bullet outside the screen, then everything else becomes a cigar or umbrella, if you like. Okay. Now you squeeze the cigar to a one-dimensional higher thing, one-dimensional higher thing beyond this bullet. Okay. What does this mean? This means that by dimension reduction, an n-dimensional anomalous topological order can always be realized by as the boundary of a one-dimensional higher anomaly-free topological order. Okay, this is very important. So any topological order can be realized the boundary of a one-dimensional higher anomaly-free topological order. Okay, because this one-dimensional higher thing can be realized by lattice model, because this can be realized by lattice model. Okay, you just do a dimension reduction of the lattice model. Okay. Moreover, we can argue that this one-dimensional higher anomaly-free topological order is unique. Okay, so this which is shown to be unique. Okay, and it will be called the bulk of X. Because it's unique, so we can give a name called the bulk. We denote it as ZX or ZX or like this. The superscript means dimension. Okay, because this one-dimensional higher of X, right? So the dimension is n+1. Right. Okay, we can also give a picture representing this relation. So this is the topological order. I will just label as A. N is superscript, N is the dimension, and its bulk is denoted as ZA. N+1 is dimension. But this how to understand the geometrical of this picture. This bullet can be understood as a topological order defined on the open N disk. Okay, and this ZA is denoted as this ZA is an open N+1D disk. Okay, so the topological order is a concept defined on the open disk, basically. All right, once you have this picture, you can trivially derive some consequence. For example, let's use one n. N is just dimension. Just one means the trivial n-dimensional topological order. Okay, a product. Well, if you know physics, you probably know what the product state means. If you don't, then you can forget about it. Okay, just trivial topological order. Okay, then we have immediately some consequence. If the topological order is already trivial, its bulk must be trivial. Okay, because that's pretty obvious, right? The second one is that if A is anomaly free, if and only if its bulk is trivial. So if A is anomaly free, it means that it can be realized by a lattice model of the same dimension in the n dimension. Then the n+1 dimension bulk is completely empty. So the bulk is trivial. Okay. Another interesting fact is very interesting is that if you consider a topological order A, then you consider its bulk, then you consider the bulk of the bulk, then the bulk of the bulk is always trivial, because look at this picture. A is the non-trivial topological order. It has a non-trivial bulk. Okay, that's not a problem. But look at the bulk of the bulk. It's completely empty, because the bulk is anomaly free. Because this is anomaly free, so its bulk is trivial. Okay, so I want to give a remark to this fact is that remember that so the statement of the bulk of bulk is trivial is somewhat due to a famous statement that the boundary of a boundary is empty, and we know that the boundary of boundary is empty. Is the origin of the homology theory, right? So in this sense, we expect a non-trivial categorification of the Euro cohomology theory. Okay, sorry. That's it, just a remark. All right, so okay, I have 2 minutes before I stop for questions. Okay, so let me give you some example of the bulk. Now consider a D-1 domain wall. Okay, this is dimension. D-1 is dimension. It's a domain wall between two topological orders, which both are n-dimensional. Okay, A, B. Okay, you can look at the picture. Okay, A is topological order, B is another topological order, and D is the D-1 dimension, which is sitting in between them. Okay, but then you can do a double folding. You can fold the B to the other side of D. Now on the left side, you get a double layer system. There are 2 layers, right? One is A, another is time reversal of B. B bar just means time reversal because the orientation was flipped after you do the folding. Okay, then this side is completely empty. Okay, I use the trivial topological order set here. Okay, so it means that the bulk of D is nothing but the 2-layer system, A tensor B. Okay, I use the box tensor to describe the the stacking of two layers. Okay. Okay, one special case of this is that when A, B, and D are the same, means that consider Cn as anomaly-free topological order. Then the center of C can be viewed as a double system here. Okay, so this is Cn, and this is just the trivial domain wall. This is not, this Cn minus 1 just means trivial domain wall inside the C. It means just artificially regarded codimension 1 line inside the topological order as something of codimension of something n minus 1 dimensional topological order. Then you do the double folding. Then you got the bulk of this C n minus 1 give the double layer. Okay, we're gonna use this a lot. Okay. Let's see. Do I have? Can I finish my? Oh. Oh, okay. Let's see. Can I finish my?
First part.
Yeah, I think it's time to just for me to stop here, just in case you have questions.
Okay, thank you very much. So good. Is there any question or comment? So I have several questions. So I missed the definition of ZAN or something. ZN.
Oh, the definition of Z is just a notation for the bulk. So for every topological order, there always a one-dimensional higher anomaly-free topological order, which is the bulk of the X. But we argue that this bulk is unique. I didn't show you the argument, okay? But just trust me on this. So given the topological order, there is a unique bulk.
No. Then ZNXN is integer?
No, Zn is an integer. That's corresponding to the dimension.
Oh, yes.
And the Zx is just a notation of the bulk of N. So maybe this picture is better. This is a picture. This is a topological order, and from previous slides, I argue that there is a unique bulk of this topological order.
What is A in this case?
You might ask, what is A? Well, let's just treat it as a black box for now. In different cases, they're very different. In different cases, A is very different. So I for now I just want to treat it as a black box. Later on, I want to give you some example what the mathematical is A. It could be a fusion category, it could be something.
What is AN?
What is AN? A is just some kind of topological. A is just a label for a topological order. N is its dimension.
N is the dimension.
Yeah.
And ZAN is?
ZA is bulk, is one-dimensional higher bulk. So that's why its dimension is n plus 1. This dimension is n, right? This dimension is n plus 1.
Box. ZA is box.
Yeah, ZA is the bulk of a physical system, many-body system.
So then you consider twice GN plus 1 and GN and AN.
Well, it's just maybe this notation looks confusing to you. Actually, this notation have some meaning, but anyway, my looks confusing to you. Let's see. Yeah, maybe I shouldn't use ZN. You can forget about the ZN here. The superscript for Z can be ignored. Okay, so maybe that will help you, I guess. Well, the reason I put it there is just sort of imitating cohomology theory. So in some sense, Z can be viewed as some kind of a differential. That's why I put the Z n plus 1 there. Just try to remind people that mine looks like a cohomology theory, the differential in the cohomology theory.
Oh, cohomology.
Yeah, but it's just similar to cohomology. You don't need to know cohomology theory. You can forget about it. It's just a remark. I'm not gonna use it in my talk. Yeah, it's just a remark.
So yes, in the case of cohomology, that guy is module.
What? I'm sorry. What's your question?
In the case of cohomology, that guy is module or additive group usually.
Oh yeah. In this case, yeah. This case is very, very different from that case. It's very different. So that's why it's a non-trivial categorification of the Euro cohomology theory. I have no idea how to build this cohomology theory. Okay, it's highly non-trivial. Okay.
Category.
Yeah, it does not have an additive structure, or it does not have a linear structure. I don't know how. I just I just want to remark that the bulk of a bulk is trivial looks something familiar to people, right? It sounds like cohomology theory, even though there's no linear structures.
Okay. So other comment or other question? I think
Excuse me.
people much more familiar.
Excuse me.
Please, Professor.
Excuse me.
Yes.
Unfortunately, I missed the first 10 minutes of your talk. But what is topological order? So that's the keyword.
Okay, the topological order is a gapped quantum system at the zero temperature here. So there is no mathematical definition of topological order, but
no mathematical definition.
But
yeah.
Are you a mathematician?
No. I'm from physics.
Oh, you're from physics. Oh,
yeah.
Then that's trouble. I think this can be viewed as physical definition. So that means. So let me restate the definition of topological order. So topological order is a gapped many-body system at zero temperature. So since it's gapped at zero temperature, only relevant thing is the ground state.
I see.
So just like a fraction quantum Hall.
Yeah. So I'm asking. So you're interested in classification of the topological order, right?
I'm interested in that, but that's not what I'm gonna talk. This is not the focus of my talk. In my talk, I'm gonna talk about the relation between the bulk physics and the boundary. I'm gonna talk about the boundary bulk relations.
Your ultimate goal is to classify topological order. Is that right?
I'm gonna talk about all dimensions essentially, but the 2 plus 1D is.
Yeah. I see.
Yeah.
Okay. Thank you very much.
Yeah, you're welcome. All right, shall I continue?
Yes, maybe other question? Okay, please proceed. Second part.
Oh yeah, so maybe because there are people coming late, so maybe let me just use 2 minutes to recall what I did. So topological order is defined in this way. Then I argue using dimension reduction, any topological order, if it is anomalous, it can always be realized, always realizable as a dimension, as a boundary of a one-dimensional higher anomaly-free topological order. And moreover, this one-dimensional higher anomaly-free topological order is unique. Okay, you have to trust me on this. I won't provide any proof of this fact, but you have to trust me on this. Then, since it's unique, then we give a name of this, just called bulk. Okay, the bulk of X, because it is unique. So we can give a notation for this, right? I'll just use ZX. I just use ZX to denote it. Okay. Moreover, sometimes I will write a superscript. The superscript means dimension. Okay, because X, the dimension of X is n, then its bulk is one-dimensional higher, so it's n+1. Okay, so then I give two example of the bulk. For example, given an anomaly-free topological order Cn, you fold it. Okay, you simply fold it and create a gap domain wall. You create a gapped boundary of a double layer system. Okay, then you can say the bulk of this dot you created is simply a double layer system, which is given by Z tensor Z bar. Z bar means time reversal for physicists. Okay, this is time reversal because the orientation was flipped. Okay, right? From originally it was on the right, you flip to the left, the orientation was flipped. So the bulk of Z. So what is the Cn minus 1? Cn minus 1 just means you forget you have an anomaly-free topological order. You just pick a codimension 1 line, codimension 1 manifold inside the disk, and you simply view anything, any observable living on the line as something of n-dimensional 1, n minus 1 dimensional topological order, and it has to be anomalous, right? Because its bulk is non-trivial. Okay. All right. So if you have more questions, you can stop me. All right. Okay. Once we have the bulk, I want to introduce a very interesting notion. In physics, perhaps nobody have studied this kind of can we define a map from one physical system to another? I don't know whether anyone have thought about this, but if you're a mathematician, you want to think about this type of questions. How to define once you have a notion, you want to define a morphism between this type of two of such notion. For example, you have an algebra, then you want to know what is algebra homomorphism. Now the same thing happened here. Given two topological order, Cn and Dn, n is dimension. Okay. Now I want to define a morphism between two topological order. Okay. Well, you can consider gapped. Okay, a gapped quantum phase, that means topological order. But in the end, you will see that the gapless is also fine. Okay. But let you for now, you just think about the CD are both gapped, so that they are topological orders. Okay, how to define a notion of morphism between these two? We don't even have a mathematical description of the topological order or gapped quantum system, right? So it's difficult to start from mathematics side, but from physical side, you can define this notion. How to do it? Okay, so I will define the notion by the following way. You consider a gapped domain wall Fn between the bulk of C and the bulk of D. Okay, n plus 1 is the dimension. Look at this picture. Okay, so you start from Cn and its bulk must be Zc, right? By definition. Now you introduce a domain wall between the bulk of C and the bulk of, you introduce a domain wall Fn between the bulk of D and the bulk of C. All right, so this is physically legitimate. All right, now you look at the this bullet, the right one. You look at this 3. You fuse this 3 in the following way. So this is just a notation of fusing the 3. So that means you can look at the 3 from far away. If you look at it from far away, this 3 thing fuse as a boundary of the bulk of D, right? So a boundary of ZD is nothing but D. So we require them to be D. So here is the requirement. Once we choose an F such that Fn fuse along the bulk of C with C give you D. We call this F morphism. Okay, it might look strange if you have seen this for the first time. But what a good thing about this definition is that you can immediately see how to define the composition of two morphisms. If we have a F map X to D, C to D, and a G map D to E, we can easily compose them by the following picture. Look at the Fn. Fn is by definition morphism from C to D, because look here. Here is a bulk of D. So this whole thing can be viewed as D. Okay, fused to the D. Okay. Now you do another G, then this whole thing fused to E. All right. Now what is the composition? Composition simply be fusion of these two. Okay. Fusion of Gn and Fn fuse along the ZD that produce a domain wall between Ze and Zc. So by definition, this defines a morphism from C to E. Okay, that's the composition. That's very, very natural. All right, let's give some examples. So what is the identity morphism between two topological order, for example? So is simply defined by the trivial domain wall in the bulk. Okay, this is a bulk. This is a bulk. You take the trivial domain wall. Notice that this boundary was defined. So as long as the trivial domain are sitting in the neighborhood of the boundary, you viewed from far away, this simply fuse together. And they have to be the trivial, have to be the same boundary. Because this is a trivial domain wall. Okay, so this is the identity morphism. Okay, next non-trivial one is the following one. We can define a unique morphism from the trivial topological order to a non-trivial one by the following picture. Okay, now the Cn here is viewed as a domain wall of the bulk of C and the trivial topological order. So this is a domain wall. Okay, look at they're essentially a similar picture, but here this is a trivial topological order of n dimension. And now you fuse these three together. You fuse these three together. What do you got? This is trivial. This is trivial. You fuse them together. You still get Cn, right? So that gives you a morphism from a trivial topological order to Cn. Okay. All right. These two are pretty trivial. Now I give you a non-trivial one. Now there is a canonical morphism from ZCn. So ZC is of n+1 dimension. The ZCn is just view the trivial domain wall in the like this one. You know, this is a bulk of C. This is a bulk of C. This is a trivial domain wall inside the bulk of C. Okay, just view ZC artificially as a n dimension, 1 dimension lower. Okay. Now, using this picture, you immediately see that this define a morphism from ZC tensor. This tensor means stacking, like stacking, okay? Just stacking of these two to Cn. Why is that? Look at this picture. What you do is just, you have a Cn and you have a bulk. Then you fold it, okay? You fold it in this way, okay? This become a bulk, right? Now I claim that this is a well-defined morphism because then you need to show by fusing the whole thing, using this thing, fusing all this thing together, you should give a Cn, right? By definition, if this is true, then you obtain a morphism from here to Cn. Why is that true? Well, that's easy, right? You just stretch it, re-stretch it, then it become a Cn with a bulk of ZC. That's it. So if you fuse this, if you fuse all these things together, you simply got C. Okay, then you obtain this morphism. You got the sound. All right. All right. Next, I want to tell you is that once we define this M, we can also define a triangle. This triangle contains 3 morphisms. One of them is identity. Okay, the trivial one, tensor C, is still the Cn, and here is identity map. Okay, identity map is just this side, because identity morphism is defined by the trivial domain wall inside the bulk. But on the other side, you have another morphism, which is defined as a, on this side is 1, is a trivial topological order mapped to a non-trivial topological order, which is ZC. On the other side, on the other factor, C mapped to C as identity. Okay. Now we want to show that this triangle is commutative. Remember, we already defined the composition of morphism, right? You write out the composition of these two, you got this one. Okay. Now I claim that this composition equal to identity. This is simply an identity, which is trivial one. Look at this. This is trivial because the only thing you need to do is to stretch them out. Then you got this immediately. Okay. So this triangle is trivially commutative. So you probably seen this triangle before, right? Might sound familiar to you. Now I claim this pair, ZCN together with M. The M is what I defined here. Okay, this morphism M. Okay, this pair is universal in that given another X topological order, given of ND topological order equipped with a morphism F. F is a morphism from XC to C. Okay. Then there is a unique morphism F prime from X to ZC such that the following diagram is commutative. Recall that this universal property is what we have discussed before. This is the same universal property of center. Okay, so this theorem simply tells you that the ZC is the center of C. Okay, this theorem simply tells you is the ZC is the center of C. Okay, now how to prove this? Actually, the proof of this fact is somewhat tautological. Let me just sketch it a little bit. I won't. Should I give all details? Okay, I have 10 minutes. Okay, let me sketch it. Okay, so first I want to tell you why this triangle, this bottom triangle, why the bottom triangle is commutative. Look at the bottom triangle. You write out this composed morphism. You got this one. Okay, remember F is the morphism is defined by domain wall. So if you write out this composed morphism, you got this one. Then on the other side, you have an identity morphism. Identity morphism is simply given this one, right? It's just trivial domain wall of the block, okay, inside the block. Now you look at this picture. These two are the same. It simply says the two bullets connected by the orange line. Okay, this orange link this two, right? Simply says that this thing must equal to this, must equal to the trivial domain wall. Okay, so you write it out. It must be the Fn tensor fuse along this Zx with X must equal to ZCn. Okay, we have this condition. But if you recall the definition of morphism, you immediately see that, look at this formula. This formula simply tells you that Fn define the morphism from Xn to Zcn by definition. Okay, so because look at this F prime, so you got a F equal to this F. Okay, so you got this F prime. So from this picture, we immediately obtain this F prime, which rendering the diagram commutative. Probably it's hard for you to see why the diagram is commutative. Only thing you need to check, only thing which is slightly non-trivial is this triangle. So I'm gonna show you why this triangle is commutative. Okay, you write out. So let's check why this triangle is commutative. Okay, I'm gonna exhibit this triangle. So this triangle. Okay. Now on the one side, you can compose this morphism with this morphism. Then you write it out. It looks like this. Another side is you got an F, right? What is the F morphism? If you write it out, it looks like this, right? Now I want to show the triangle is commutative. You simply need to check that these two are equal. Are they equal? Take a look. You simply smoothen this zigzagging thing, then you got this immediately. Okay, they're tautologically equal. Okay. So what are we? So what's the miracle happen? So we this give you the proof. I think let me summarize. Let me summarize the miracle. Okay, the miracle is this. The miracle happened on this definition of morphism. Once we give a proper definition or correct definition of morphism between two topological order or two gapped or gapless quantum system. Once we give a correct definition of morphism, then the universal property of center, then the block is satisfy the universal property of center simply pop up automatically. Okay. So in a sense, it's trivial. It does not rely on how you describe the Bach physics and the boundary physics. You don't need that. Okay. Let me summarize. So what do we have proved? We have proved. So previously I tell you that to consider both Bach as gapped and boundary as gapped as well. But if you look at the proof, you can see that the theorem holds the Bach equal to the center of boundary, regardless whether the Bach is gapped or boundary is gapped or gapless. As long as the following dimensional reduction process works, as long as you have something Zx, a Y, and can be fused along a one-dimensional higher thing. Okay, and after fusion, it become a domain wall between another two n+1 dimensional things. Okay, as long as this works, this dimensional reduction things work. This theorem holds. Okay, let me see how long do I have to, okay, I still have 6 minutes. Okay, that's good. All right, so let's see the power of this theorem. So this theorem, it looks very quite strange for many people because I think physics is hard for physicists to think about physics instead in terms of category theory, in terms of universal property, in terms of morphism between two physical systems. That's not in the physics vocabulary, but I want you just bear with me with this new way of thinking. Notice that the way of thinking is so powerful is that we don't even know what the Bach is. We don't even know what the mathematical description of the Bach is. And we don't even know what's the mathematical description of the boundary either. So, but the theorem works, okay? So let's take a look at some special cases. Now, when the Bach is gapped, this theorem says is the center of the gapped boundary. So now I will give you a special example. In this concrete examples, both Bach and the boundary have a concrete mathematical description, okay? So the first theorem is that for 2D means spatial dimension, a gapped Bach admitting a gapped boundary, okay? In this case, the gapped boundary is mathematically described by a unitary fusion 1 category, okay? And the gapped Bach is mathematically described by a Drinfeld center of A. So what does this mean? So in this case, the center, look at the center here, okay? Now the center is placed more concretely as a Drinfeld center of a monoidal category. Okay, fusion category is special case of monoidal category. This theorem have a generalization for an ND dimensional. This is 2D, okay? For general ND gapped boundary, gapped Bach admitting gapped boundaries. The gapped boundary is mathematically described by a unitary fusion N category, A, okay? And the gapped Bach is mathematically described by the Drinfeld center of A, okay? So in this way, it's concrete. Now I want to give you another example. This example might involve too many things. I won't give details, but I just another example of a gapped Bach and a gapped boundary. This leads to a classification of an ND topological order with an on-site symmetry defined by a unitary symmetric N category R. I won't go through the detail, but just want to tell you that this theorem play a very important role in the classification because look here, you look at this condition involved in this step in this classification theory, both involve the center. So this is the center of R and the center of A. A is another fusion N category. Okay, I won't go through the detail. Just want to give you a feeling that this theorem also control topological order with symmetries, with on-site symmetries. Okay. All right, this is a gapped Bach and the gapped boundary. Now I want to give you another non-trivial example. It's a gapped Bach and the center of is a center of a gapless boundary. Well, this has become highly non-trivial. Okay, so it's well known that 2 plus 1Ds or 2 plus 1Ds. This is space-time. Sorry, topological order can be described by a pair where C is a unitary modular tensor category. It's some kind of braided tensor category, okay? Describing the fusion and braiding property of particle like topological excitations, and the C is a chiral central charge, okay? If the theorem works, there should be a categorical description of any chiral or non-chiral gapless boundary of 2 plus 1D Bach, such that whatever the categorical description is, its center must equal to C by our theorem, right? By this theorem. Whatever the Miss theory, I denote the X sharp. I don't know what it is, but center of it must be the Bach. Okay, if you believe it, you can work it out. It turned out that a gapless boundary of a 2D topological order is completely described by a pair. The first one is the unitary rational VOA. V is a unitary rational VOA. If the boundary is chiral. If the boundary is non-chiral, it is a full field algebra. I won't explain it. It's just the chiral and anti-chiral combined together, okay? Such that the mod V is a UM modular tensor category. Another data is this one. So mod V is the category of V modules. Okay, mod V is the category of V modules. So category of V module is unitary modular tensor category. This result depends on the representation theory of oh, I didn't say what a VOA is. No one stopped me. VOA is abbreviation for vertex operator algebra. Okay, but this is not so important. The only focus on is the categorical part. This notation is an enriched mod V enriched the unitary fusion N category obtained from the pair via the so-called canonical construction. I won't explain the detail of this, but the key point is the Bach equal to the center of boundary. Mathematically, it just means the Drinfeld center of this enriched category. Remember, this is a notation for enriched fusion category. Okay, it also have a notion of Drinfeld center. introduced by Zheng Hao and myself in this paper, we show that this is still true. Okay. So this is an example of gapped block and gapless boundary. Now you probably wonder, what about? Okay, my time is almost up. So let me just. So last example I want to show you is that what about the gapless block and the gapless boundary? Yes, in this case you can. There are examples of this by study 1+1D rational CFT. Since the time, my time is up, so I won't go through the detail. I just want to show you that there is a precise mathematical description of or classification of open-closed CFT satisfy certain boundary conditions given by precise mathematics. I'll skip it, but the point is, by a theorem, the closed CFT is the full center of the open CFT. Okay, we still got this result. And what's the full center? No matter how the full center was defined, it's still defined by the same universal property. Okay, so the full center, the universal property of the full center is the same. Look at this diagram. It's completely the same as before. Okay. All right, I'll skip the last slide. Thank you. That's the end of my talk.
Thank you for nice talk. Is there any question or comment? So, if possible, could you back to the example part? So you give us some example about Z and A.
Yeah.
So where is that example?
I can hardly say it's an example because I just tell you that it's a Dreamfield Center. So Dreamfield Center will treat it as an example in my talk, but I won't define it because I already defined it in some sense because I give you the universal property. So I mean, all the center appeared in my talk. For example, the full center, or the Dreamfield Center, they all defined by this same universal property.
Oh.
So I mean, they defined by the same universal property, but they live in a different category.
Different category.
Yeah. So it all depends on what this object means and what this morphism means. If this object means algebra and the M means algebra homomorphism, then this just means a Euro center. But if A is a monoidal category, M is a monoidal functor, then the center is the Dreamfield center. Let me give you another example. If A is a braided monoidal category, M is a braided monoidal functor, then this center is Milgre center. So there are all kinds of different centers. Well, let me give you another example. If A is a A infinity algebra, M is a A infinity algebra map, then this center is so-called the derived center, which is also called the Hausdorff cohomology. So there are all kinds of different notion of center.
Also, I have another question. So, could you explain the relation with some physical model?
Well, in this, yeah, I can explain but I'm not sure. Not in my slides. Let me see. Physical models. Okay, so I don't have a. Oh, maybe I have. Okay, so maybe I have a picture which is some living in here. I didn't show you this picture. In this case, you can use a physical model to justify this. So you can explicit. So given in this case, let's take A to be a fusion 1 category. Okay, let A be a fusion 1 category. Now you can use a lattice model called the Levin-Win model. You can construct a lattice model, realize the bulk, and realize this gap the boundary as well. It's called the Levin-Win model. Using that lattice model, you can compute the topological excitation inside the model and inside the bulk, then it can show that it's given by the dream field center of A. You can also compute topological excitations living on the gapped boundary, then show that they are given by A, which is a fusion 1 category.
Sorry, I cannot find what is the relation with physics? So
How to connect to physics?
yes.
Yeah, I didn't show you the lattice model because that would be another talk, because it's very hard to explain the lattice model construction. And that would deserve another hour to explain how to construct a lattice model to realize the dream field center of A as the category of topological excitations of the 2D topological order. I think that deserves another 1 hour talk to explain. Yeah, yeah. But if you know, well, I can give you, but it depends on how much you know. Do you know toric code model?
I don't know, sorry.
Okay, yeah, well, then toric code is simpler, but that's a special case of level 1 model, but that also take another maybe 20 minutes to explain, I guess. Yeah, I just want to give you some general feeling about the general philosophy of a boundary-Bloch relation in terms of the statement, the Bloch is the center of the boundary. Okay, now I want to give you a feeling about this, or maybe some confidence about this, because it's true in many examples. Okay, that's all. Yeah, there's no concrete physics example in this talk.
Okay, as a comment or question?
Okay, so may I ask a question?
Yeah, sure.
My name is Kanno from Nagoya University. So maybe I'm afraid that my question is slightly different from main focus of your talk, but
okay.
When do you say the topological order has an anomaly?
Yeah.
So what is the definition of anomaly in your system? I mean, I want to try to connect your talk with the first talk in the morning by Professor Matsuo.
It's right here. So a topological order is called anomaly free if it can be realized by a Hamiltonian lattice model with a local interaction in the same dimension. And it is called anomalous if otherwise. So if you're a physicist,
I mean, so the definition of anomaly free is, clear, but anomaly has
anomalous.
So if you find some lattice model, you say anomaly free, but it is possibility is it is not so. We are not so wise to find lattice model. The criteria of anomaly is somewhat difficult, right?
Yeah, there are some way to describe the anomaly. So in the end, you can, by the theorem we provided in this talk, you can give another definition of anomalous is that the center is trivial. If the center is trivial, then it's anomaly free. If not trivial, it's anomalous. For example, so
okay. That is more clear. I mean, if the center is non-trivial, you say it is the topological order is anomalous.
Yeah.
Okay.
That's the one way. But if you're a physicist, I would say think about the topological insulator, and there are non-trivial edge mode, right? Non-trivial boundary modes. Mm-hmm. Then the boundary mode can be viewed as some kind of a topological phase, which is anomalous because its bulk is non-trivial.
I see.
Yeah. For example, fraction quantum Hall, right? Fraction quantum Hall, you have a topologically protected gapless edge. That gapless edge can be viewed as anomalous CFT. It is anomalous.
But in the case of quantum Hall effect, that anomaly is characterized or detected by some kind of index, as was talked by Matsuo. So my asking, so in your case, anomaly is detected by some kind of index or something.
Yeah.
Your answer was the anomaly was detected by some kind of center.
Yes.
But not index, right?
It
Or
can also
indices.
be viewed as an index, but it's much more powerful in the sense it's completely characterized the anomaly. The center contains all the information of the anomaly.
But can you define some indices, index of the center?
Yes, you can also do that. Pick any partial information of the center can be viewed as indicator. For example, quantum dimension or other things.
So the dimension
matrix, or there are many indicators. Yeah.
So dimension. So for example, dimension of the center is some index. So
yes.
Okay.
Yeah, but there are many others. For example, ST matrix of the center category can also be served as an indicator of anomaly. So there are many different indicators, but each indicator is not a complete description of anomaly, but the center is almost complete description of anomaly. It's not only indicator, it contains all the indicators.
Of course, I know. The center has more information. Okay.
Yeah.
Okay. In any case, thank you very much.
Yeah.
Okay, thank you very much. So then we have enough discussion time, so we can move to the next talk. Thank you very much.
Yep. All right. Thank you.
So could you take a session of the next talk?
I'm gonna. Oh God.
And the next speaker, final speaker is.
So let's see.
Who is the next?
Me?
Yes, Professor.
So next speaker, right?
Yes.
Moriyoshi, right?
Yes.
Yoshi Moriyoshi. Yeah. You wanted me to share it or?
No. Please take share. Yeah. Not chair. I'm not the chair. Next one.
Okay. So it's 2 minutes past 4. So you have 2 more minutes past 5. Okay. Let's start from now. So our next speaker is the Hitoshi Moriyoshi. The Ginsburg-Wilson index theorem for quantum walk on the integer lattice. Welcome. You can start now.
Oh, okay. Do you hear me?
Yes.
Right?
Yes.
All right. So first, I'd like to thank the organizers, Hayashi-san, Kanno-san, and Yanagida-san, for the invitation and also the opportunity of talk. So this is based on the joint work with my collaborator Toshikazu Natsume in Nagoya Institute of Technology. So this is a picture of Sir Michael Atiyeh and Isadore Singer. Atiyeh is left and Singer is right. And since I'm specializing in the Atiyeh-Singer index theorem, the connection with the non-commutative geometry. So in the first part, I'd like to give you a flavor of the Atiyeh-Singer index theorem. So I'd like to state the index theorem in the full strength. So take closed manifold, say M, and take the 2 vector bundles, complex vector bundles, E0 and E1. But if you wish, you forgot take trivial line bundle. That means the working on the functions. And take the elliptic differential operator. So the Dirac operator acting on the spin bundle, which already appeared in the Matsuo-san's talk, in the first talk. That's the typical examples. Then the such operator, the elliptic differential operator, it's called a it is a Fredholm in this case, since M is the closed manifold. That means the kernel of D and its adjoint is finite dimensional. So that case, we can define the Fredholm index denoted by I in D. That's the difference of dimension of these two kernels. Kernel D, dimension of the kernel D, minus dimension of kernel D star. It's a joint. So the Atiyah-Singer index theorem gives us the A formula to describe this, the index of the elliptic differential operator, which is, so take the, we start with the M, but M is the equipped with some the A Riemannian metric. Then such a manifold admits the Riemannian curvature two form, denoted by R. So that is the two form with values in the endomorphism of the tangent bond. So the locally, this is the matrix valued two forms. And take the Todd function denoted by TD. That's simple, simply Z over 1 minus E2 minus Z. So this function is called the Todd function, and which appears in the study of the Riemann-Zeta function and also other places. And the first part of this, the integration, Todd I over 2 pi R, is just to take this curvature form, the two form, and substitute into this Todd function. So as I explained, the locally R is the matrix value differential forms. So the locally we can make a addition and also multiplication with the wedge product of differential forms. So since the Todd Z, this is actually has a power series. So we can substitute this R into each powers. And we get, since if they multiply the differential forms enough, that vanish. So the Todd, we get well-defined Todd form, Todd substituted by this one, and which is denoted like this, the Todd I over 2 pi R. And this is first ingredient, and they determined from the manifold itself, nothing to do with the operator D itself. And second part, this is an invariant of the elliptic differential operator D. And there is a so-called symbol that's denoted by sigma D that defines in this case, the endomorphisms on the tangent bundles, TM. And resulting in the so-called Chern character form. That is again the even dimensional, even degree forms. I'm sorry, this is TM typo, this is TM. But it's compactly supported, turned out, or at least integral. So even if the TM is non-compact, this integration makes sense. And it turned out this integration is equal to the index of this given elliptic differential operators. So that is the Atiyah-Singer index theorem, index formula, which was proved in 1963 in the last century. But this is definitely one of the most celebrated mathematical theorem in the last century, and it is very useful in everywhere in the geometry. And at this point, I feel like making a digression to the law of Planck. So he actually lived long until I cannot see this one. The 1947. Yeah, so 89 years old, he passed away. And why I want to talk about the Planck's formula. In fact, there the third function is involved. So the physicists, maybe we have many physicists in the audience today, and they interested in the spectrum of the black body radiation. So they just fix the frequency nu, or they maybe just consider the frequencies between the nu and nu plus d nu per unit volume. Then we are interested in the total radiation, the intensity of radiation. And in the classical theories, let U be the energy of the radiation per normal oscillation. That means just the total energy, the total intensity of the radiation divided by the number of the normal oscillations. Then according to the law of the equipartition of energy in thermodynamics, this is the very famous formula. U must be K times temperature, where K is the Boltzmann constant. Then the total, the energy, so that means this U times the number of the normal oscillations. The amounts to the 8 pi nu square over the c cubed, c is the velocity of the light, times kT. And it is known as the Rayleigh-Jeans formula. So that's the classical formula. But it turned out this formula is not suitable to the equipment, I mean, experiment. And Wien, found the suitable formula given as follows. In his formula, U is equal for some constant B and A, nu times e to the A nu over KT. And actually, this fits very well to the experimental data when the frequency is large or temperature is pretty low. So this is the graph of those the functions. The red one is the Rayleigh-Jeans formula. The red one, actually this diverges finally. But Wien's formula, as frequency goes to the infinity, the convergence goes to the zero. So makes like this, the graph of this one. But the Wien's formula is very suitable to the experimental data. However, not exactly the fitting, as I said. So the Planck considered proposed some formula to interpolate connecting these two formulas. That's the black graph. And when the temperature gets higher, the peak of this frequency here is a little bit increasing. And that means this function tends to approximate this red one, the Rayleigh-Jeans formula, red one. And also blue one is the Wien's formula. That is exist. And the Planck's formula seems to interpolate these two formulas. And recently, the astronomer says the Betelgeuse in the Orion in Japanese, that may make a supernova explosion. But in any moment, they say, but in any moment for astronomers is 100 years, 1,000 years, so not in any moment for us, but anyway, that's the getting bigger and bigger, it seems. And they can measure the temperature, and it's supposed to be just the 3,600 and so on. And this temperature is just correspond between this the 4,000 and 3,000 here. And the peak is the really the visible light, the regions falls into this one. And that really explains the reason the Betelgeuse really looks red. And the Planck's the interpolation formula, it was submitted in the last year of the last century, the 19th century. And that was given by the h u is equal to the h nu divided by the e to the h nu over kt minus 1. And where this h is a new constant, now called the Planck constant. And in fact, as t goes to the infinity, this recovers the kt, that's the Rayleigh-Jeans case. And also when t goes 0, we can recover the Wien's formula. So really interpolating these two formulas. And this formula, in some sense, really looks like the Todd function, but a little more argument. So the h nu and kt, has the same dimensions. Dimension means in physics, unit measurement. So h nu over kt, which is as an exponent of the denominator, say x, that's in physics dimensionless. That means the kind of the number. So if we rewrite this formula, that means the Planck's energy divided by the classical energy. That means the Planck's energy U divided by the classical energy was kT, so divided by kT here. Then this dimensionless x appears in both numerator and denominator, and turns out to be x over ex minus 1. This is nothing but Todd function, but not x, but substituting the negative x. So in that case, in the Planck's formula, the Todd function already appears, especially if we take the ratio of the Planck's energy and classical energy. That is exactly the Todd function. So this seems the kind of coincidence. And one more coincidence is the pretty interesting point is if you knew the proof of Atiyah's single index theorem, you understand the reason why this Todd function appears. That means the Todd function, this is not the negative Todd function, x over ex minus 1 is a ratio of Euler class, so-called, in the K cohomology theory and ordinary cohomology theory. And the left-hand side, Planck and the classical, that means as a constant, the Boltzmann and constant, Planck constant. So also there, the K and H appears. So this is really a coincidence, I think. However, not coincidence part is this K ratio of the K theory and the cohomology is kind of the contrast between the discrete object and continuous object. In fact, the ordinary this H star M, this means the drum cohomology. So it is evaluated by the integration. So essentially, this is the theory of R. So this is related to the continuous object. However, K cohomology, this is denoted by the K star M, that is by definition, the constructed out of the vector bundles on M. So in some sense, vector bundle, the isomorphism class vector bundle. So this is the discrete object. So that means the total function easily appears when we work on the discrete object as well as the continuous object. And this was exactly the situation in the Planck's law and also the Atiyah single index theorem. So that was the explanation of the Atiyah single index formula, and also some coincidence or connection to the Planck's law. And now I'd like to explain the earliest and would say the simplest index theorem in mathematics. Our setup is as follows. So take the circle, maybe simplest closed manifold of one dimension, and take the L2 function, which is the all L2 functions. The space is denoted by L2S1. This admits the natural orthonormal basis. That is the exponential to the IMX over the square root of 2 pi. To make the norm 1, we have to divide this. And this is denoted by the E to the actually down n, sub n. Then we have so-called the Hilbert transformation. With this orthonormal basis, the definition of the Hilbert transformation is very simple. For positive, including 0, orthonormal basis vector, just leave it as it is. For the negative one, negative En, multiply by negative 1. So that's the definition of F. And then also take the continuous two functions, A and B, and make an operator T, which is equal to A plus B times F. So just A means the make a multiplication. So multiplication operator is noted by simply A. And here this is the composite of two operators, B and Hilbert transform F, which we call the native operator. In fact, the original paper, this native is in yes, as I mentioned here, one of the member of the famous native family, but not Emmy native, not Max native. He is a Fritz native. And this is I call this the native operators, but in the original the papers, the Fritz native use degenerate the Hilbert transform. That means just for the E0, he just assigned the image the 0. But anyway, as far as the index concerned, that's what we are going to do. Then the index is the same, so we don't care about this point much. Then the native index theorem is stated as follows. So take the A and B and assume A plus B and A minus B is invertible. That means the function, continuous function means the function with values in the complex number. And invertible means never gets 0. So the image is contained, the set, the complex number minus the origin. Then it turned out this operator, the native operator, is Fredholm, and the index of this operator is computed as the degree of this map. Since both A minus B and A plus B is invertible, so the ratio is also invertible. So that means this is the mapping from S1 into the C minus 0. So we have well-defined winding number. And this winding number is denoted by degree. So this turned out to be the index of this native operator. And it seems this is the earliest the paper to state about this kind of the index theorem.
Professor Moriyoshi, is that a good time to stop for questions? It's 20 minutes.
Just let me finish this example quickly in the 2 or 3 minutes.
Okay.
So the set A is the T over, I cannot see this, but maybe T over T plus I. And another one, D is the I over T plus I, right? Then the native operator turns out to be the capital T is the 1 over T plus I times T plus I F. And the F is the shifted by by a Fourier transform. They consider as the operator on the L2 function, the R real. Then this corresponds to the sum operator. That means the differential operator, usual differential operator, self-adjoint one, the plus the sign functions, C over the C bar, the absolute values. But this is can be perturbed to the annihilated operator, or if you wish, we can make a direct computation. Then it's easy to verify it's the index. So since everyone knows the index of the annihilation operator, this is just 1. Kernel is 1-dimensional and co-kernel is the 0-dimensional. So the index is 0. On the other hand, A minus B over A plus B, this is nothing but the T minus I over T plus I is a carry transform. So the degree is 1. So number is really coincides. So this is the kind of the simplest example of the index theorem. Okay, I stopped the first part.
Yeah, so any questions? So you have this another index theorem. What's the relation between this index theorem with Atiyah-Singer index theorem?
So formally we can say this is the odd dimension version of the Atiyah-Singer index theorem.
Oh, I see.
So originally the Atiyah-Singer index theorem, at least to get the non-trivial values, the M has to be even dimensional manifold, as long as the differential operator is concerned. However, in this case, the Hilbert transform, that's the order 0 pseudo differential operator, or so-called singular integral operator. Then we can make the odd index theorem on the odd dimensional manifold, in this case S1. So this is the case.
But is it the most general form of Atiyah-Singer index theorem in all dimension?
Yes, that's the issue of the second part.
I see, okay. Any other questions?
I have a small question. So maybe you give us some picture about some spectrum.
Yeah,
I think.
wait.
You show the picture for, yes, and the previous one. Yes. So I could not find what the relationship with this picture and your topic, your talk.
This is just a graph of the Planck's energy. Oh, sorry. Here. This times the number of the oscillators.
Yes, of course.
Not exactly U, but U times the number of the oscillation.
Yes, this is somehow relationship between the nu and energy. Why this kind of function is very important in your talk?
Since third function appears. So here the point is, if once divided by KT and get dimensional invariant, we
Yes.
recover Todd functions.
Yes, we have this function. Yes.
Yes. So the point is the Todd function appears in both Planck's law as well as the Atiyah-Singer index theorem.
Oh, this function is called Todd function. Todd function. And
Yeah, this is
appeared
precisely
in,
Todd negative X.
this function is appeared in your formula.
Atiyah-Singer index theorem.
Atiyah-Singer, could you show me?
Here.
Oh,
Do you see my point?
Okay, I understand. Thanks. Okay. Thank
And
you.
second point is this Todd function's ratio z over 1 minus e to the z is the ratio of the discrete object versus continuous object.
Oh, I see. Okay.
Here, this is point.
Oh, okay. Thank you very much. Thanks.
Morio-san.
Hi.
I noticed that this Todd function is an integrand of so-called dilogarithm function. Is the fact mean something to you?
Yes, also Todd functions is very useful in the study of the zeta function as well. So I'm not quite sure. However, as I said, this Todd function ratio is in other words, the polynomial world versus exponential world. So the maybe dilogarithm, if there is such the pictures, the polynomial versus the exponential. In other words, the Cauchy distribution and Gauss distribution, that's another word. Then the Todd function easily appears. So I wonder there might be some link or connection to the dilogarithm theories, but at this point, I'm not quite sure.
For example, if you integrate from minus to infinity, you get some pi square over 6 famous Euler's formula.
Yes, the integration, the values of Todd function, that's has a little distance from ours. Ours is once the substitute, in my case, the substitute differential form, and make an integration over the original manifold. So a little different, however, they may be related. I'm not sure, quite sure.
Okay, thank you.
It sounds very interesting.
All right, any other questions? Okay, if not, I think it's a good time to continue the talk. Yeah.
Okay. So one more, there is maybe the simpler index theorem. That's called the Toeplitz index theorem. So again take the same the orthonormal basis and take a projection, so-called the Z-gate projection. That means for positive one increase 0. That's the leave as it is, and then cut off the negative part. And then we consider just this image. This is a subspace of the total L2 functions, but still it's the infinite dimensional Hilbert space. On this space, we can define so-called Toeplitz operator out of the continuous function A. That means simply first make the multiplication by A, then the compress with this projection. Since the multiplication that usually does not preserve this image, so the image easily gets out of the image of the projection. However, compressing with the P, we get operator from the image of P into the image P. That's the Toeplitz operator. And we have the index formula for such operators, which is due to the Goldberg decline and after the Fritz method found in the 1958. That is the most simple. The index of this Toeplitz operator is, if it is invertible, that means if it is never vanished, then index of the operator is negative degree of A. Very illustrating example is the case of the A is the e to the k times ikx. K is a fixed integer. Then this bond, the bullet, just correspond to the basis of the image P, since the image P is the projection onto the positive space. Then the multiplying by the A, so then 0 basis goes to the K basis, 1 basis goes to the K plus 1, and so on. So this is kind of the dilation. So we can easily see this has no kernel. However, whole kernel is the K dimensional. So that index is the negative K. And it's easy to see negative degree of A is just negative K. So they coincide. So this is maybe the simplest, the odd dimensional index formula, but found later after the Fritz, the net. Now the issue in the second part is just try to discretize the Atiyah single index theorem. So that's our example is the so-called quantum walk. So maybe I should say make some the explanation on the quantum walk, but I leave it maybe Nishimura-san or the Rugal-san. So just quickly I goes to our setup. So we take the Z integers in R and make a L2 sequence. So that makes the Hilbert space. And also the drag function at N, the characteristic function, makes the orthonormal basis of this space. And then the T, this is just translation. This makes the denote the forward shift. That means the drag function, characteristic function at N goes to the characteristic function at N plus 1. So just one shift. And then out of T, capital T, we make the so-called shift operator. That is a keyword of the quantum walks. But anyway, that's the operator of the L2 space times tensored with C2. So in other words, this total Hilbert space is just on each the bond integers, we have the two-dimensional, the complexity vector space. So that's the total space, namely the L2 sequence with values in the vector space, two-dimensional vector space C2. And the gamma shift operator is given by 1 over square root 2 of the 1 T star negative 1. And if one is of course, quite used to the quantum walk, just this reminds of the so-called the Hadamard gate. And the point is later to find the non-trivial index theorem is this Hadamard gate makes the universal gate in the quantum walk, our quantum computation theory. So that was the key point to get the non-trivial index theorem on the quantum walks. And it was also in some sense, the surprise to me. And then another ingredient, so-called the coin operator. That is pointwise multiplication by A, B bar and negative 1. And the A, B satisfies these relations, where A is a real number and B is the complex number. So here, with the contrast to the gamma, this is just pointwise multiplication. Namely, this is the kind of the bunch of the 2x2 matrices. And the important property is both gamma and C is involution. Involution means this operator is self-adjoint and square is identity. So the nature is very much different. This is the translation is involved. This is C is just pointwise multiplication, but they are both the involutions. Square is equal 1. And one more, we assume the C, the pointwise multiplication, has a limit at the plus infinity and negative infinity. Then the U, it's denote the composite of the gamma and C is called the evolution operators. And this evolution operator is really considered as the quantization of the random walk. So that this is the reason why we call this system as quantum walk. But anyway, this U plays important role. In fact, not quite U. Out of U, we make U minus U star. If you are familiar with Witten's supercharge theory, we call this the supercharge operator. And turned out this is an anti-commuting with the coin operator C. Then we can make a so-called chiral operator, Q plus. That means so C is the involution. So there is the two eigenspaces, +1 eigenspaces, -1 eigenspaces. So the compressed Q with, this is the +1 eigenspace projection. This is -1 eigenspace projection. So if we write Q into the 2x2 matrices, we just took the off diagonal part and the left down corner. That is Q plus. And also assume this the limit at the plus infinity of negative infinity is not 1 square over 1 over 2 square. That is related this number. So the coefficient, this coefficient is not the limit of A. Then it turns out this is the Fredholm operator, and Fredholm index is given by the plus or -1 according to the case of this, or 0. And that was due to Suzuki and Tanaka. They found in the last 2 years ago. And this was the first index theorem found for the quantum walks. And also this was a starting point of the index theorem, the joint work with the Toshinatsume. So let me review the setup again, or now C star Z. This is by definition, C star algebra generated by the translations. Then this translation and the assume take some unitary element on this C star and make the shift operator again. So here capital T was replaced by some unitary operator. Then since this is unitary operator, gamma again involution. Square is 1. And we have the same coin operator. And then evolution operator and the supercharge and chiral operator. Our index theorem is, in this case, there is a so-called the symbols of the chiral operator. Two symbols, according to the limit which tends to the negative infinity or plus infinity. Then, if this chiral operator is Fredholm operator, then this index is equal to the degree of the ratio of these two symbols, which is invertible. So that's really the mind of the Toeplitz index theorem, as well as the Nater index theorem. And actually, it turned out this index theorem is strongly connected to the Fitz-Nater's picture, the index theorems. And as a corollary, this index theorem contains the last Suzuki-Tanaka index theorem. That's what I want to explain. But point is, the proof is done by using the so-called big picture of the K theory and K homology. So to explain this, I have to make a very quick review in 5 minutes. So it's really, time is running out, but I try. So the quick review, first, K theory or K group is defined for a given C star. And second point is the K group of C star algebra is nothing scary. So I just keep the explanations, but the first, we have 2 groups, K group, K0 group and K1 group. And K0 group is constructed, this is a abelian group and makes the cohomology theory a homology theory. And this is defined out of projections of matrix algebra with coefficients in A. A is the C star algebra. So the projection means just the adjoint is the same and square is equal to itself. Then the K1 is this is even simpler. Definition is just make a ZL infinity of A. That's a direct limit of GL and A, and take a connected component. Since this is topological group, connected components, the set of connected components makes the abelian group. And this is by definition K1. So I said nothing scary. It's easy to define. At least the definition is very is done very quickly. And then point is the very intriguing point is once given the short exact sequence of C star algebra, starting with the ideal I, A, the middle part, and quotient. Then there is a long, but long means just six-term exact sequence of K theories, starting K0 of I, K0A, K0B, then so-called there is a connection homomorphism, goes to the K1 of I, then K1 of A, K1 of B, and again connection homomorphism and coming back to the starting point. And turns out to be this is a long exact sequence, just like the usual homology theories. So this is very important and intriguing. And one example. So take the L is the old bounded operators on the infinite dimensional Hilbert space. Then such the algebra contains in some sense the unique ideal, closed ideal, namely the ideal consisting of the all compact operators. It's denoted by K. Then we can make a quotient. It's called Kalkin algebra. So we have short exact sequence starting K, then bigger space, all bounded operators, and quotient. Then the resulting six-term exact sequence is the four groups at 0, and finally just K0 of K and K1 of the Kalkin algebra remains and turns out to be Z. And this K, the compact operators K0 is just take the projection that turns out to be finite dimensional projection. So just take the trace or rank of E. So that makes the isomorphism with the integers. And the K1 of Q turns out to be the isomorphic to the integers out of this connection homomorphism. But meaning is the invertible element, that's the definition of the K element of K1. Invertible in Kalkin algebra is nothing but if this element is given by the pi projection of T, T is a Fredholm operator. So in terms of the capital T, the integer is given by just the Fredholm index. So out of this six-term exact sequence, we can read off the Fredholm index as a connection homomorphism between Kalkin algebra and the compact operators. So now the second the ingredient is so-called extension theory. The conclusion is extension theory gives K homology, not K theory. So far I talked about K theory. That corresponds to in the topological case, the K cohomology. Here, the counterpart, K homology. The K homology is given by the short exact sequence, which is called the extension of A, which means the final group or the algebra is just A. And starting the ideal has to be the compact operators. So the middle, this is kind of unknown, we can change, but all such extension makes the abelian group if the C star algebra is separable. And this is now called Brown-Douglas field theory. The all set of this extension makes is equipped with the abelian group structure, and especially if you take the C-star algebra of the continuous function of such space, then it turns out this is isomorphic to the K homology theory of X. And the beauty of this Brown-Douglas field theory is the pairing. There should be a natural pairing between cohomology and homology, but this pairing between extension and the K1 group is just given by the image of the connection homomorphism. Since the out of E extension, we have 6-term exact sequence and connection homomorphism from K1A to the K0. That is the integer, that's more to the integers. So just substitute U here, then we get integer. So the connection homomorphism turned out to be the natural pairing between K homology and K cohomology. So summarizing the Fredholm index we studied, however, this can be rephrased in the big picture. First is the pairing between homology and cohomology theory. And second is eventually just saying, but rephrased in terms of the connection homomorphism. But this is also the same as the Fredholm, the index of some operator, connected to the U. And finally, we want to find some topological or geometric formula to give this the Fredholm index. So this is kind of the false, not primitive, but the false. But the ingredients makes the generalized the index theorem. And when we worked on the K homology and K cohomology, really we recapture the Atiyah-Singer index theorem and the natural pairing. So I skipped those one digression. So I should talk about the Ginsburg-Wilson algebras. I'm very happy to answer it if you have a question, but I just skipped and just to define so-called the Ginsburg-Wilson algebra is C-star algebra generated by 2 involutions. So in our setup, quantum walk, we have 2 involutions, coin operator and shift operator. Then we can make the Ginsburg-Wilson algebra out of those the shift and coin operators. And also for the Nader index theorem, we can construct so-called Nader algebra, some extension. Then our index formula, this is already described, the index of the chiral operator is given by degree of the ratio of the 2 symbolic functions. It can be interpreted as the pairing between this invertible symbol and so-called the pullback of this Nader extension, which was induced in the inclusion of the Ginsburg-Wilson algebra into that one. And as a corollary, we can recover the Suzuki and Tanaka theorem. So the last part is very quick, and I had to prepare some problems, but I just finished here. Thank you very much for your attention.
Oh, thank you. Thank you for the very nice talk. So any questions? I can ask the first one, I guess. So from the second part of the talk, it looks like the index theorem can be cast into a very general format. I think it's much, because you're working in the algebra setting, it's much more general than the original index theorem, right?
Right, that's in the context of the non-commutative geometry a la Kahn.
I see, yeah.
You make use of the K theory of the C star which may be non-commutative,
Yeah.
the C star algebra, and the K group, K homology of C star algebra.
So I guess it's also covered the previous, the another index theorem and the topless index theorem as a special case, right?
That's right, in the big picture.
I see.
That's already done by the, maybe I should mention the Baum, Douglas, Fillmore, or the Kasparov, John Lowe, Higginson, and so on, and you name it. Yeah, there are many persons working on that. Yes.
I see. Well, there one thing that remind me of something very interesting is that the pairing between K-homology and the co-homology, because I know Hertzsprung-Riemann-Roch theorem can also recast into some kind of a pairing of certain non-degenerate bilinear forms, which have a geometric meaning. I forgot the detail. Which have some kind of a physical meaning as a Carty condition in topological field theory, two-dimensional topological field theory. So it looks like since Atiyah single index theorem and the Hertzsprung-Riemann-Roch are deeply related, so I was thinking maybe the Atiyah single index theorem should also have some kind of a topological field theory interpretation, isn't it?
I think so. In fact, the Albrecht Gomet and also Getzler, they gave the sign of the alternative, the proof of the Atiyah single index theorem by using the Feynman integral in the past space.
Oh,
so they definitely are the Atiyah single index theorem, or the proof is related to the anomaly. And also in the careers, they made the proof of in the general theory. So far, the restriction of the Atiyah single index theorem is they just work on the compact operator, closed operator, strictly speaking. But we can extend the index theorem to the complete manifold, like the n-dimensional, the Euclidean space, and so on. So yes, the answer is yes. There are many attempts to generalize the Atiyah single index theorem and try to make a connection to the physics theory.
I see. All right, thank you. Any other questions?
Okay, may I ask a question?
Yeah,
sure.
In the last report, you mentioned work of Ginsburg-Wilson, right?
Yes.
And they are physicists, right?
That's right.
And Ginsburg is connected to the archive, right?
Yeah.
Okay, so my understanding correct. Then I think the work of Ginsburg-Wilson is related to renormalization group, right?
Yes.
So how renormalization are related in your
right.
renormalization
First,
group is related to
better than me,
theorem.
However, Ginsburg-Wilson relation is the perturbed the chiralities, and it turns out using by this if we are working just on this case, the Ginsburg-Wilson operator is the form of the 1 plus minus unitary operators, where unitary satisfy this kind of the reflection the relation. So in this case, we are just working on this case, but in this case, this operator satisfies, turns out the Ginsburg-Wilson operators. But the origin is if you take the gamma and also the gamma times u, these terms turns out to be involutions. So point is, in our setup, everything is amounts to just the 2 involutions. And maybe in the fuzzy sphere case, that's a finite dimensional approximation of the S2, the 2 spheres. That case also they made 2 involutions, but point is no relation between them. So the operator generates so-called universal Ginsburg-Wilson algebra. So that's
sorry. So the important point is just that relation.
Ginsburg-Wilson point relation. Is for 2 involutions, no relation. That's
I see. I see. So in the sense, the I mean, the renormalization is nothing to do with your argument. Just the important thing is algebraic relation, right?
Not quite. Here I didn't explain, but in such the universal Ginsburg algebra, we can make so-called the double index, so-called chiral index class and double index class. So if it's not Ginsburg-Wilson case, we just get one index. However, in the Ginsburg-Wilson case, namely we have two kind of the independent involutions. It turns out we have two index, chiral index and double index, which correspond to that index studied in the lattice gauge theory. And so this is the kind of
I'm sorry. So putting my question differently, I mean, what is the origin, a physical origin of your two involutions?
That comes mainly out of the fuzzy sphere. So fuzzy sphere is by definition, they take a all continuous function of the F2 or the L2 space of the continuous function of the two-dimensional sphere. Then once we decompose this function space into the irreducible representation of the SO3, this vector space isomorphic to the direct sum of the irreducible representations. And it turned out this is the also direct sum of the endomorphism of some irreducible spaces. So we can equate the non-commutative product on the continuous functions on the S2. And this object is called fuzzy sphere. And then this is direct sum of the irreducible representations. So we have the kind of the limit of finite dimension object. And this finite dimension object is called fuzzy spheres. And they admit two different involutions, the left Dirac operator and right Dirac operator. So that's the most important examples, and the example we keep in mind.
So did Ginsburg-Wilson originally consider the fuzzy sphere?
Now, later, many Japanese are involved.
I see.
Those Japanese found the operator satisfies this original Ginsburg-Wilson relations. Once you get to the unitary operator, Ishibashi, Iso is Aoki.
So lattice people found that.
That's right.
Realized on fuzzy sphere. Okay. Thank you very much.
Okay. Any other questions?
Yes, I have one question. Good evening. What would happen if your coin operator has different limits at infinity, not only constant, but if you consider more complicated system? Can you extend the framework? For example, if your coin operator becomes periodic on both sides?
That's a very good question. And in fact, related to this problem on third. This case, we just considered assumed there exists a limit at plus infinity and negative infinity. That means we considered the compactification of this lattice, so-called two compactification. Here, so the lattice is compactified, putting just the plus infinity and negative infinity. And out of this, the two compactification, we get this so-called the negative extent. And that's the situation in the Suzuki, Tanaka, and ours. However, looking at this the extension from the viewpoint of John Law, who developed developed the index theorem further which is applicable to any complete Riemannian manifold, or he considered the non-compact space and many various type of the compactification. So your question is exactly comes to this point. So the two-point compactification of Z, that's I would say, easier. The biggest one is the text-on compactification. This is huge and very difficult, almost impossible. So even periodic case, we still have the very huge part, and which is related so-called the Higgson's compactifications. So that's of course very intriguing and the direction we should seek. But yes, I'm very happy if you're interested in this the kind of the research of this direction. We do not find some result yet, but definitely we are interested in.
But there exists some quantum work having periodic asymptotic on the left and on the right. This exists, but there is no index theorem based on them yet.
Not the explicit formula. We should have. That case, the point is for example, in the case we here, right? The Nathan extension involved the 2-point compactification as well as the blueprint. That means that here we're just considering this compactification times the translation. So if you choose the periodic function here, replace this part, then the 2-point compactification is replaced the bigger compactifications. In that case, we have to find the suitable, the simple class algebra and extensions. And then we have to make the pairing between the extension and some object. That would be the index theorem we seek for in this case. But I do not have the explicit form at this point. Maybe in this area, you know better than me. Yeah.
Okay. No, thank you. I believe something is doable indeed.
Thank you very much.
Okay. We're over time, but I don't want to stop people to ask questions. So maybe so the organizer maybe shall we stop for Remo or
yes, okay.
But anyway, so I want to if you still have questions, we can maybe admit one more questions, just last questions. Okay, if there is anyone. Any questions? Okay, if not, we thank speakers and we let for further questions we can use the Remo, right? To if you want to discuss with the speakers again. All right. So I will leave the Master, are you gonna take over? Because I'm only chair for this talk, but you are the chair of the whole thing, I guess.
Okay, thank you very much. So
thank you.
Now we want to close today's session. So then we prepare a Remo session for free discussion. So please move to Remo.
Okay.
So I put
is the Remo address?
Yes, I put address in chat for Remo. Please click that address.
Okay.
Thank you very much.
Thank you.
Thank you.
Nice talk.
Thank you very much.
Thanks.